Indigenous science, groundwater tracing, and Obsidian. Welcome to Geology Hour. I'm Alyssa Smith.
I'm Carrie Gordon.
And I'm Gabriel Finn.
So hello everybody. So this is my segment, Geology in a Nutshell, and we're going to go over a few different articles today. The first one is going to be blending science and indigenous knowledge. And the second topic is groundwater tracing of cave systems in Southern Oregon. So our first story is the longer title is Blending Science and Indigenous Knowledge to Tell an Estuary Story. And that was from EOS last December, which was last month. The focus of this article was all on furthering scientific research by collaboration between scientists and Indigenous experts. So the story focuses on the tribe that's involved with this is the Coquel. You may be familiar with the town and the river of Coquille, but the tribe pronounces it Coquel. So I wanted to make sure that we got that right off the bat. And I wanted to highlight some of their missions, that essentially they're dedicated to the health and the well-being of their tribal community, promoting health and wellness, taking care of their elders, practicing responsible stewardship of the land, and education. And I'm going to make sure and include a link to their website in the notes in case anybody wants to go in and take a look. As far as where the Coquel tribe is located, so this is a map showing different tribes and languages. And if we look down here in Southern Oregon, this is where part of the ancestral lands of the Coquel are located. So what they mentioned on their website is that their ancestors didn't leave them maps showing borders of where they were at, and that they know a lot about their people from oral tradition. There's also been archaeological evidence saying places where that they harvested food and materials and places that they held sacred, but they're currently centered in Southern Oregon near Coos Bay. So as far as the science part of this goes, this started off as work by a biogeochemistry student at University of Oregon who was looking at vegetation in the Coos Bay estuary in response to European American settlement. And the way that this kind of collaboration started was really interesting, I think. So there's a pretty established connection between the Coquel tribe and U of O scientists, and they were apparently having dinner and were talking about kind of the connection between salmon and the land. And it's known by the tribe that salmon don't just pass through Coos Bay, but they're actually bringing nutrients from the ocean along with them to the rivers and wetlands in the area. So that is what kind of spurred the student who was doing the research to kind of start to look a little bit deeper into how these things are connected. And so the collaboration, this ended up being a group of faculty from the university, including people from the science departments and from Indigenous studies. And together with the tribe, they proposed that the rapid decline in salmon populations were evident in the rivers. So essentially having less salmon in the river meant that nutrients were not being returned to the river, and that this impacted vegetation and animals. So as for the experiment, that's what this picture is here, is they extracted meter-long soil cores to kind of look at a timeline of the land's response to fluctuations in salmon populations. And what they looked at is things like chemical indicators, basically. They mentioned carbon to nitrogen ratios and stable nitrogen isotopes as indicators for fluctuations in nutrients over time. And what they found is that kind of what they expected, areas that, or kind of like the opposite of the way that it was phrased initially, is that areas where there had been restoration efforts recently are areas where they saw higher carbon to nitrogen ratios, not rations. I don't know why it's rations there. Higher carbon to nitrogen ratios. And this aligns with a greater salmon population. So the restoration, just to summarize, the restoration shows up in the nutrients in the rivers as, correlating with these higher salmon populations. So essentially what that means is that when salmon are more abundant in this area, it's very likely that that is not just coincidental, but they're actually playing a role in improving the nutrient cycling in the rivers. So there are some limitations that they noted with using soil cores, and this is a picture actually from the field when they were taking those cores, is that these cores will give a lot of information about one specific spot, but they can't tell you kind of how the chemical and biological components there ended up at that location. So eventually the goals are to not only get more information, they mentioned that they're going to be trying out something called environmental DNA, which I think my notes are on the last slide. There we go. Yeah, so it's called environmental DNA, where they're looking at remnant DNA from waste, from remains or excretions from animals in the river to look into where salmon have lived in the river and when. So that'll just be a little bit more robust of a data set. Now, the goal kind of with the research is to not only inform restoration efforts, so they can see if, that this is something that is a valid reason for for restoration, but also that they want to continue the collaboration. And there was a quote from one of the researchers, or this is the one of the people quoted in the study, but essentially talking about science and talking about indigenous ways of knowing is important, because a lot of the indigenous ways of knowing complement a lot of the science that exists. So thanks for saying what SHPO was. I worked at the Corps of Engineers.
That's okay.
I had to know that.
It's just one of those things where we throw out all these acronyms and we don't always know what that is. And that State Historic Preservation Office is here in Oregon, and it governs our archaeological sites. So one of the things that I was wondering about with the salmon is the fish bios that I worked with in the Coast Range often talked about species and diseases that they might carry in. They're fine in one river system, but if the fish tries to go up a different river system, it takes that disease up there, and it causes issues with the fish health. But this whole thing with the nutrients actually is pretty darn fascinating, because with this riparian restoration, or in this case restoring within the estuaries there, that kind of raises a whole question of once we get salmon coming back in numbers, are they going to be coming back into a healthier environment? And I think that's what that study was starting to prove.
I think so. Sometimes these EOS articles are based on like a published article. This one I think is still in process. It linked to a recent AGU presentation that they had done at the, I think it was the meeting in December, where they were presenting their findings. But I think that there's still going to be time before like the final paper would be put out. So I think this is still developing. It's very current.
Okay. And did you get a sense, Gary was curious, did you get a sense about how deep they were going with their cores?
So they are going a meter.
Okay, so not very deep at all.
Yeah, it's pretty close to the surface.
Okay.
Which I do not know much about deposition in estuaries over time, so I wouldn't be able to say how long, how far back in time that core would go. I'm guessing that, so they're looking at, basically European colonialization, which that would have been like the past 200 and a bit years.
Right.
So it doesn't have to be that long.
Yeah, as opposed to having been impacted by tsunamis and earthquakes.
Essentially, what they're finding is that there's a lot of harmony between what people in this area have known for hundreds, if not thousands of years, and the science. And so, we need to be looking at these things as a holistic, practice, because otherwise we're just trying to reinvent a wheel that doesn't need reinventing. These things complement each other so well, and all it takes is having some conversations. Like literally over a meal is how they figured this out. They have known for hundreds of years that the salmon bring stuff with them. Like it's not like the salmon are completely independent from where they end up. It's like they live their lives, beginning in the ocean, and they bring that with them. So it's like not this hugely unexpected thing, but it's something that, people might ignore.
Paul said, I'd recommend our friend Dr. Anjana Katwa's book, Whispers of Rock, on the subject of what is Indigenous knowledge. Ooh, hey, that's, I'm going to have to write that down before I forget.
Writing that
That
down
sounds
too.
like a good one to read.
On to the next bit. So this is a pretty sharp turn away. I mean, we're still staying in the water, I guess. So this is a recent USGS publication that came out. And it's essentially a report talking about groundwater tracing, where they were looking to see where water was coming from in some of these systems. So big long title, we'll just skip that and go into the next bit. So what is this? This report is a multi-year groundwater study that was done at the Oregon Caves National Monument and Preserve, as well as the cave next door. Which is a literal name, that's not just the one next to it. So the information that's included in this this report is mostly, I didn't finish the slide. I was going to take this one out, that's all right. So it includes maps, pictures, data. There's a lot of information in here and a lot of things to look at, which I am not going to knock people for wanting that. I want pictures to look at. So really good stuff. Now, where is this? I don't ever like to assume that everybody knows where everything is. So essentially the Oregon Caves Monument is down in southern Oregon, almost at the border into California. It's in the Siskiyou Mountains. And so this green bubble on the map shows the Klamath-Siskiyou region, and this little pin here shows the approximate location of the Oregon Caves. And basically the caves are within Marble Rock Unit, which marble, we don't really think of marble and Oregon at the same time. At least I don't with my igneous bias. But this is part of that whole Klamath-Siskiyou terrain. It's within the Rattlesnake Creek terrain. And when we have marble rock, some of you know, we'll get karst topography. Now, Alyssa, what is karst topography? Karst topography is a very specific, it's like a fun term, I think. But it's essentially when you've got limestone, dolostone, rock gypsum, these evaporite-rich rocks, you can have dissolution that leads to essentially sinkholes, caves, and underground drainages. And this is a pretty old picture that was on one of the websites. Maybe it just looks old because it's an older camera. But karst topography, people like to crawl through that stuff. Not me. So why is this study important? Essentially, the root of it is that a lot of karst systems, the hydrologic systems, are interconnected. And so looking at areas around the cave systems can be important so they can understand how environmental factors can influence water quality in the systems. So the Oregon Caves is a system that's the Oregon's longest cave. So it's about 3.03 miles, and it contains basically an entire river in it. They call it the River Styx, which I think is a really cool name, knowing bits about mythology and whatnot. But cave next door, I could not find a picture of that. And it's a pretty, it's a lot shorter. It's 837 feet long, and it's a river cave that was just discovered in 1999. So it's not something that's been established nearly as long as the Oregon Caves. I know 1999 unfortunately wasn't last year, but it's, as far as caves go, that's a pretty recent discovery. So this study, what did they do here? So the scientists that were working on this project used fluorescent dyes to map these really complex underground pathways through the cave systems. So they were looking for specific recharge areas. And this particular picture is a dye called fluorescent. I think that's how it's pronounced. There's a few different ones that they used, and I'll explain why. Pretty interesting seeing it there. But so this is one of the maps from the study. Just kind of an example of some of the stuff you can see. So this shows the different lithologic units, which are shown in the different colors. And let me kind of highlight, there's different units in the area, cave passages, but then they also show the cave system itself. They show trails nearby, and they show places where they actually did the dye injection. So you can see like the black trace there shows the cave system underground. And obviously the places where the springs are, like coming out of the ground at the surface. So they picked a number of different sites where they were going to inject different dyes. And I'm not going to try and read them because they've got very complicated names. But essentially they use 4 different types. And the reason why they use different dyes is because they've got different wavelengths. So the different emissions, like signals that they can use through spectrophorophotometer, which gives them the spectrum of the dyes. And the reason that this is important to have different dyes is that if there are multiple of the different chemicals that come through at a certain location, they can see, oh, this has this tracer and this tracer. So if they use the same one, they wouldn't be able to pick out exactly which of those spots it was coming from. So the picture here shows the scientists there doing the dye injection. They mention a lot in there about this specific PPE, basically like I think it's Tyvek suits and gloves and stuff to make sure everything is very clean. It's pretty neat. So the way that they did this is they started multiple injections simultaneously at a few different spring locations. And they did this over, 2 years, a few different times of year, and basically trying to see whether the water systems traveled to the Oregon cave system or to the cave next door, or both. They found that there's 2 distinct areas that don't overlap between the Oregon cave and the cave next door. So the recharge area for the cave next door is slightly east, and it's even a slightly larger footprint, even though the system, like the river itself, is a lot smaller. And then there's essentially no overlap between the 2 systems, which is really interesting. And so what they found in this is that, they delineated 2 different recharge areas and found that these 2 karst systems, even though they are right next door to each other, are not actually hydrologically related to one another. And they also were able to see, there's very little human development in this area. I think it's like, one of them, it was like 99% evergreen forest, and the other one was almost as much, and they had another land classification, I can't remember. But what little human impact there is not expected to significantly impact these recharge areas. So I think that, I don't know if they said it outright, but I think it's cool to see this here at a place where, we wouldn't expect there to be much of a human imprint, but they can see very clearly that this method, they can see exactly where things are coming from. I don't know if they're going to use that in other places that maybe do have more human development, but it's good to know that the paths and minimal roads out there are not impacting the water system. So that's about it. That's my bit.
Thank you, Alyssa. Awesome as always. Do you have a feeling, does Northern California, being part of the same topography, have similar karst caves?
Oh, definitely. Yeah, sorry, I interrupted. I got so excited that I knew the answer. Wait, I know this one. So there's, if you go further south, I've always seen it when I've been driving and I've never stopped, but there's a whole cave system that you start, if you're driving north on I-5, you start to see signs around Shasta Lake. Sorry, you heard a Greyhound ear flap there. You start seeing signs around Shasta Lake for the Mount Shasta Caves. My dogs are very vocal tonight. I'm sorry. Normally I'm in a closed office, but we're just making do.
So, moving on. So, Gabriel, is going to discuss his work on rhyolite obsidian sourcing of artifacts in the Northern Great Basin, which I am so fascinated to hear what you have to say. So take it away.
All right. Hello, everyone. My name's Gabriel Finn. I'm a master's student at PSU currently. My work is in igneous petrology and geochemistry, specifically in rhyolites and obsidian. And this is my talk about rhyolite and obsidian sourcing of artifacts in the Northern Great Basin. Just to start, this first photo is of the Bear Valley. And this is actually looking at Strawberry Mountain, which is one of the main sources of obsidian in Oregon. So just to start out, what is obsidian? So the typical definition of obsidian would be like a naturally occurring volcanically induced glass, right? It's black. It's transparent and it breaks easily. The more geochemical definition is a high silica rhyolite with over 70% silica in the matrix. So the rest are these elements that we will be tracking the geochemistry of later on. But typically obsidian is a rhyolite that it has a glassy texture. Okay, it's densely welded and it has low vesiculation. And some obsidians actually have pretty high vesiculation. And we'll talk about that later. But when you have all of those characteristics in a rhyolite that's non-devitrified as well, that's typically what you see as an obsidian. And so if you look behind the background of this is another major obsidian source. And this is the big obsidian flow that I've personally taken and been to all these locations. This is the big obsidian flow at the Newberry caldera. And so that's one of the major sort of volcanic igneous provinces in Oregon. So let's talk a little bit more just in general about obsidian in Oregon. So in Oregon, silicic volcanism is extremely widespread. It covers a vast majority of eastern to central Oregon has silicic volcanism, as well as basalts, as you guys may well know. But we have these rhyolites sort of popping up in between the basalts. So the major regions are the Cascade Range, as everyone probably knows about. The high lava plains, that's a little bit lesser well known. The Basin and Range margins, and also the Newberry caldera, as we just talked about. So those are kind of the major sources of these rhyolites and obsidians, as you see. This photo that you see, I personally took. So this is of one of the sources in the Cascades called Obsidian Cliffs. And to get to Obsidian Cliffs is about a 14-mile round trip hike, and it has 5,000-foot elevation gain. So to get some of the samples and to get to some of the locations provides a logistical challenge as well. One of the major sort of concepts about my research is that obsidian devitrifies into rhyolite. And so basically what happens is on an obsidian dome, obsidian is erupted or the rhyolite is erupted and it's sort of viscous and it's moving across the ground and eventually it hardens. Now, over the time of, we think, weeks to months, certain portions of these obsidian flows are becoming devitrified over time, which you can see in this picture. The major differences in these obsidians and rhyolites is not geochemical, but it's actually what my professor likes to say, mostly textural. And so these are actual physical differences. So a lot of the time it's differences in the viscosity of the magmas in different layers, differences in the porosity, or even slight distinct crystal arrangements, or in some cases it is chemical, but it's by very minute amount of elements that causes to get devitrified. And again, this happens within weeks to months of the original flow being erupted. So as you can see here, this is another very classical geology example. This is in the Roadside Geology of Oregon book of the Paulina Lake Dome, also known as the Summer Lake Source. And as you can see, there are these white sort of bands of volcanic tuff separated by these dark bands of obsidian slash partially devitrified rhyolite. And so you can really see the difference in layers and the difference in stratigraphy of this rhyolite dome. And that's why it's a very famous classic example. And it's also a major obsidian source for the Summer Lake area. So I also wanted you guys just to see that one as well. It's pretty cool. So let's get into the actual sourcing. Previous work in rhyolites and obsidian sourcing. Craig Skinner has his obsidian sourcing laboratory, and that's a great research if you guys are interested. He does basically everything to do with obsidian. He has multiple thousands of samples that he's taken and locations that he's plotted. We have someone on my committee team member, Dr. Connolly at the University of Oregon Museum of Natural History, and his research is in obsidian sourcing and sort of the anthropological interpretations of that, and also carbon dating are his main focuses, and he was the director of the Museum of Natural History as well in Oregon. And also my professor, Martin Streck, here at Portland University, he's done a lot of research in rhyolites and just in geochemistry. And he's also been a big help in sort of on the journey of the geochemistry and obsidian sourcing. And then Dr. Ford, who has done a lot of the research in the high lava plains and mapping them out and age dating of the high lava plains, which we'll see in a little bit. And he has done a massive amount of work for Oregon State. So we have Oregon, PSU, and Oregon State. They all have kind of contributed to this framework, as well as Craig Skinner with his obsidian sourcing laboratory is a major player. So I just wanted to, before we get into my research, just wanted to say some of the other research for you guys. So now starting. There's different formation types of obsidian. And before we start talking about obsidian and artifacts, I kind of want you guys just to know what those are. So you have an obsidian dome or a flow. That's like your classic, what you think of obsidian as. You have an obsidian coulee, which there are very famous geological examples of that. That's essentially a dome or a flow that is elongated down a slope. So it's very similar to a dome or a flow, but it's more massive in size. You have a vitrophere, which is essentially the same composition as an obsidian, but it forms through compressed volcanic ash. And so while what you think of a classic obsidian is sort of a viscous lava flow, a vitrophere is also an obsidian, but it's formed by compressed ash. So they actually have the same geochemistry, but different formation processes. So those are all included under obsidian. Now, the last two types are sort of lesser known, but they're also important. And that's a block and ash flow, which is where you can get giant blocks of basically secondary obsidian material that get incorporated in these massive pyroclastic flows, which may be buried further up the mountain, but they get incorporated in these pyroclastic flows as block and ash. And then lastly is fiamme, which, like I said before, most obsidians need to be non-densely welded. Well, a fiamme is essentially a pumice that is being compressed in a volcanic tuff matrix. So those can actually form obsidian balls that can be used as obsidian as well. So these are the main different ways that obsidian gets formed. It's not only by, a volcanic sort of ooze coming out of the ground that's molten. They also can form by ash and by these other processes. So in this picture, you can see here, this is actually one of the meadows of obsidian cliffs. And in this meadow, it's essentially the surface of an ancient obsidian flow that has been broken down over time. So I don't know the exact age of obsidian cliffs. I have it in my data somewhere. But basically, this flow has been exposed probably for the past, 200,000 years. And that's why you see so much obsidian on the ground here. It's basically what we call a pavement of obsidian. And a lot of the obsidian you find looks like this. Most outcrops do not look like the big obsidian flow. So that's one of the things I wanted to say as well. But this is a pavement of obsidian at Obsidian Cliffs. It's pretty cool. So obsidian is utilized as an ancient tool source kind of for two reasons. So they have really good fracture mechanics. It has conchoidal fracture, and it's really sharp when it breaks. So the ability to be flaked combined with the sharpness is really why obsidian is being used by indigenous peoples, as well as a cultural sort of history and, a tie to the environment of using these really cool looking materials like, volcanic glass. There is some sort of connection spiritually as well as functionally. And that's what we'll talk about more with the obsidian sourcing. So some of the best artifact examples in the entire US are in the Northern Great Basin in Oregon, and they're artifacts made out of obsidian. And so that's why this topic is, kind of near and dear to a lot of people. And I find it extremely interesting. And this is one of the main reasons why I came to Oregon, is kind of to get into these types of topics. So this is something I find very interesting. So obsidian sourcing, this is a picture of the XRF at my parents' laboratory. They have their own company called Wapsie Valley Archaeology. And I've been doing a lot of my obsidian sourcing with this XRF machine. So you can see this is kind of a box, and the machine is actually in the bottom of the box. This is a lead box designed to capture the X-ray beam, so it's non-harmful to anyone. And essentially, you load up the artifact or the geologic sample, and you press the button and you shoot XRF X-rays at it for about 60 to 90 seconds. And once that's done, the machine analyzes the spectra of that, and it basically reads off a composition of elements. And I take these, the ppms of the elements, and I put those into Excel. And that's the start of what the database is. So this is an example of what Craig has for his database. And these are all obsidian sources, as well as some obsidian caches and just places where he's all found obsidian. So this is really important for telling us about trade networks, mobility, subsistence, ways of life. And what I think about, this is kind of the basis of obsidian sourcing, is that all of these things, the mobility, the ways of life, are being told to us through the geochemistry of the obsidian itself by tracing these patterns. And so each one of these is basically a spot where obsidian has been found before. While this is extremely helpful, this database is a bunch of locations, and we don't necessarily have rhyolite data or the geochemistry about the rhyolites at all of these locations. And so this is highlighting that there could be more work that needs to be done. So this is the what I've been working on with the rhyolite database. And each of these is essentially a location of different rhyolites that have been collected by geologists. And so I gave you guys a breakdown of sort of the different repositories of data to where I kind of acquire this data from. So we have Swenton is in blue. She did her PhD at PSU, and it was extremely helpful for kind of getting data about this. Ford did his PhD in red, and he did his at OSU in 2012. And he did a lot of the high lava plains, so that was his major study. And then PSU people are a lot of the master's students. Their information's in green, and that's compiled from about 8 different theses that I got their XRF results from. So, in going to this slide, the Great Basin is extremely complicated in terms of volcanology. So you have the intersection of the high lava plains with the Cascades and the Blue Mountains with the Snake River Plain / the Oahes and the Northwest Basin and Range, essentially all converging on this one area, as well as the Columbia Plateau. And that creates an extremely unique ecoregion where you have this combination of obsidian deposits as well as people sort of utilizing the landscape for an extremely long time. And that's sort of what obsidian sourcing is about. So these are some plots that I made with my data over the high lava plains And the main point is that the different elements can be tracked through space and time when you have a database like this. So this is sort of preliminary results, but you can see different regions. Like up here is the Blue Mountains. Certain regions have higher elements, which essentially correlates to different magmatic processes that are happening underneath the ground when these rocks were formed. And so later on, I have a figure that tells you about the ages, and that kind of gives you an idea about how these magmas are evolving through time, which is an important aspect of obsidian and rhyolite geochemistry. So this is kind of one of the major databases of obsidian sourcing. And I made all these figures from the data. All this data is essentially, compiled into my database. And you can kind of sort of see the different obsidian sources. I thought it was interesting to show you guys. So the main ones are Glass Butte, Cougar Mountain, the Burns Green, Obsidian Cliffs, and Whitewater Ridge, which Whitewater Ridge is also known as the Strawberry Volcanics. A lot of these obsidian sources are plotting distinctly, and you can see it's ZR versus SR, so it's zirconium versus strontium. And this is what the elements that you sort of classically use for obsidian sourcing analysis. While these elements are available on XRF and ICP-MS, other elements that are used for analysis are only available on ICP-MS, where ICP-MS analysis destroys a little portion of the sample. XRF analysis does not destroy any of the sample because XRF is non-destructive. And so that's why a lot of the time XRF is needed in archaeology work, because we need the XRF for non-destructive analysis, basically, because you can't be destroying really important artifacts. Even if we really want to know what they're made out of, we have to treat them with respect, right? And conserve them. So a lot of these sources are very important to understand archaeologically. And I just wanted to give you guys your first glimpse into sort of what obsidian sourcing is like. And it's making a lot of geochemical plots. So that's sort of what it's like, is a lot of geochemical plots. So this is another plot that I made using selected portions of the Rhyolite database. And you can see here, this is Obsidian Cliffs. So the black triangles are actually data that I got from Hughes' publication study over Obsidian Cliffs from 1993. The yellow are samples that geologic samples that I personally collected from Obsidian Cliffs. And you can see when I do the analysis, they're plotting quite tightly together. So I would consider that a successful sourcing of the Obsidian Cliffs material. You can see right here, the blues and the reds and green is glass buttes. And while it's more messy, they also form a pretty distinct cluster of glass butte material. So that's another sort of can of worms, because glass buttes itself can be differentiated into 7 to 11 different parts. So I'm not as interested right now in differentiating glass butte. There's been some papers about that. I'm more interested just knowing what glass butte is in general. And then the last you can see are these pinks and purples. And these are actually from the Strawberry volcanics, also known as the Strawberry Rhyolites. And the purples are actually obsidian cobbles that I collected this summer. And so you can see that a lot of the obsidian cobbles are plotting with these rhyolites that were collected in a previous study. And so this sort of proves the idea that you can use rhyolite studies to source even obsidian cobbles. Because remember, all obsidian is rhyolite, but not all rhyolite is obsidian. So you should be able to geochemically source rhyolite and obsidian the same. So that's kind of what we see here, as demonstrated with it's hard to see, but it's called the 3 cabin spring rhyolite. And these are cobbles of obsidian. So essentially that means that obsidian is sourced to the 3 cabin spring rhyolite, which is new information. So that's pretty interesting. Next, this is actually what I was talking about before. So this is a comparison of XRF versus ICP-MS data of the entire rhyolite database. So in my Rhyolite database, we have over about 1,100 individual samples of Rhyolite/Obsidian. And you can kind of see on this plot the differences of accuracy of the XRF versus the ICP-MS. Actually, a lot of this data is pretty good. So the ICP-MS should be about 97 or 98% accurate compared to the ICP-MS. And the ICP-MS measures parts per billion, while the XRF measures parts per million. So this is kind of showing that you really only need parts per million accuracy in terms of obsidian sourcing. Sometimes for mining and other precious metal materials, they want more accurate data. But in terms of obsidian sourcing, XRF is non-destructive and it works about just as good as the ICP-MS. So that's why this plot is really important. And you guys get to see all my data points, which I think is cool. So each one of these is one of the samples in the database, and there's probably about 500 samples for XRF and 500 for the ICP-MS. So pretty cool. This is what I wanted to talk about, the Malheur National Forest region. So this summer we did field mapping in the region, and this is one of the sort of a figure I made on ArcGIS to show you guys. In the region, there's multiple obsidian sources. So this is kind of where one of the major problems with the, sort of trying to do this in real life started. We had obsidian from Burn Mountain 2, obsidian from the Rattlesnake Tuff, which is a vitrophyre, obsidian from the Strawberry Rhyolites, which I talked about a couple slides previous. We might have had a new rhyolite or a new obsidian called the Myrtle Creek Rhyolite. And then to throw it all in, there's also another kind of obsidian in the Dinner Creek Tuff that comes up in block and ash because there's a lot of incorporated obsidians from a completely ancient volcanic eruption that get incorporated in the Dinner Creek Tuff. And as a, obsidian sourcing, you have to be able to keep all this sorted out. So technically, each one of those should have a distinct geochemical, sort of profile. And as far as right now, I'm working on the Rattlesnake Tuff, the Strawberry Rhyolites, and the Burn Mountain 2 source. All have their own distinct profiles. So that is really good news. Just in terms of the getting into the high lava plains, so this is a really good figure from Swenton. And Streck, Ford, and Swenton have all done massive amounts of work over the high lava plains and sourcing rhyolites and basalts. And this is sort of the aggregated, figure from their work. And I just wanted to touch on this part. This is why mapping obsidians is so complicated. So you can see up here, the top of the blue is basically the Blue Mountains or the Strawberry Mountains. Where the 024 is, that's basically the Cascade. And what's happening is the rollback from the hotspot is interacting with the subduction zone at the Cascades. And that's actually what formed Newberry. And so that's why Newberry has so much obsidian. But you can basically track these obsidian domes across Oregon in the high lava plains. And the leading research by geologists is saying that the obsidian dome formation is a direct result of the rollback of the migration of the Yellowstone hotspot. So essentially the Yellowstone hotspot is moving, and that's creating a flow of magma underneath the plates where it's more viscous. And the hotspot is essentially emerging as these different sort of rhyolite domes, or the rollback from the hotspot is emerging as these rhyolite domes in Oregon. And those can be tracked. So that's kind of what this figure is getting at. And it's an extremely complicated process. There's been multiple PhDs written about it. We don't know everything for sure about why the hotspots are occurring, but that's the greatest and latest on why geologists think sort of the obsidian is occurring so prolifically in Oregon, especially the high lava plains. So in terms of archaeology, Dr. Connolly is sort of the Oregon expert in archaeology and obsidian sourcing. And he sort of specializes on radiocarbon dating and obsidian sourcing as well. So what his name of the game is, they source the obsidian with help from Mr. Craig Skinner at the Northwest Obsidian Laboratories. They date the soil that it was the obsidian artifacts were found in, and then they have a great indicator of when people were utilizing that specific location and what artifacts they were using. So they know if they find those same artifacts, throughout Oregon, that it's sort of the same groups of people that are either moving throughout Oregon, or their sort of ideologies and their technology has spread throughout the region. So it kind of tells you about these people. So it's really interesting. So you have a big Clovis Point up here in the right corner. I don't know if everyone can see this. You have a big Clovis Point, and you have these little points at the bottom were found at Paisley Caves, which is another major site. These are all important sites, basically. And my next figure has a pretty good, here we go. The next figure has a pretty good picture about these. So just touching in on how cool some of the sourcing is and the current theories on the archaeology portion. Western stems points date from 18,000 or 16,000 to 14,000, depending on which site that you look at. And they go all the way up to about 8,000 years old or so. And that's a really long sort of projectile point technology. So over 10,000 years of projectile point technology use in the Great Basin, which in my estimation is the longest basically use of one technological projectile point culture in the entire US is in the Northern Great Basin in Oregon. Specifically, Dr. Connolly is thinking that they're utilizing the Pleistocene lakes in the Northern Great Basin, and they have these very distinct stemmed points that they use for hunting. And his carbon dating sort of background, they're finding woven textiles, and they found some of the oldest use of fish nets alongside these obsidian points, which is suggesting a more sort of a more lifestyle accustomed to the Pleistocene lakes, essentially, in the region. So when the Pleistocene lakes dry up 7,000 to 6,000 years, ago, the way of life also dried up, so to speak. So it's a very prolific sort of culture, and it's also the hot topic of archaeology right now, is finding these obsidian points or other Western stem points and dating them is very important, as well as Clovis points as well. So you can see this kind of shape and style is more Clovis point related. So just in terms of projectile point technology, everyone, these at the bottom are, Western stemmed points. This point over here is more of like a Cody style, like later point, where these points with the curved bottoms are more what you think of typical paleo points across the US. The top ones look like more like knives, and these smaller ones are probably spear points, but this bigger one is probably a knife point. So this culture is extremely old. This site particularly is from Cougar Mountain and 5 Mile Point Cave by Paisley Caves. And just one shout out, they dated a lot of the deposits at Paisley Caves to be 14 to 15,000. And Virginia Butler from PSU did a lot of her work they dated the soil using fish bones. So that was a previous article that was talked about. I just wanted to tie that in as well. So they actually tracked the fish bones in the soil to see at Paisley Caves to see when there's human occupation before they found artifacts. So that was kind of cool. Current work and future collections. So in terms of wrapping up my thesis, I want to do a partnership with the Malheur National Forest and the University of Oregon and analyze some of the collections that they have there, hopefully with paleo, so older, obsidian points. I want to keep expanding the Rhyolite obsidian database by synthesizing samples. And I want to build up the PSU Rhyolite obsidian repository because we have a lot of samples now, and sort of get everything documented and bagged up for PSU. And the goal is to obtain a reasonable sample size of all the obsidians / rhyolites across Oregon, which I'm doing pretty good so far. So that's what I got, everyone. So questions. And also, if you have any samples of obsidian, feel free to reach out. This is my email here. And yeah, here's the references. Hopefully you guys all enjoyed.
Oh my gosh. Okay, there's a lot of questions, Gabriel. Awesome talk. In a shorthand way, could we think of the sources as being that's the quarry that everybody used when they were in the neighborhood and they needed their points to go hunting? Could you think of it as a uh, a quarry of its time? Not a rock, not like for crushed rock, but for
Great
points.
question.
So is that what your source is? Is that's a place where people hung out and picked up their obsidian chunks that they hauled off somewhere else to break up?
Great question. So the leading theory is that basically the geochemistry of the entire mountain should be consistent or homogeneous. So I want to make sure I'm saying it right. So it's the difference between homogeneity and heterogeneity. And it's actually a big sort of debate at Glass Butte on whether Glass Butte is homogeneous. But like I said, for sourcing purposes, they're relatively homogeneous.
You're saying sourcing. Are you thinking of this as being like figuring out where, like, basically chemical fingerprints for these? Is that what you mean by sourcing?
Yeah, we want to figure out which mountain came, like which artifact came from which rhyolite dome / mountain, essentially.
Perfect. Okay, that's what I thought. I didn't want to assume.
So if somebody, and this is an important one, so somebody finds obsidian artifacts out in nature, what should they do? Leave it alone, photograph it, notify who?
Great question. It depends where you're at. If you're in a national forest, take a picture of it, mark the location, and contact the nearest park ranger, because pretty sure it's like a felony to pick up anything in the national forest or
National parks.
what's the NF and the national parks as well. So do not pick anything up in the national parks.
And Bureau,
If you find it on private, I'm actually giving a different talk in April for the Archaeological Society about collector sort of efficacy. So if you're finding it on private land, take a picture of it, mark the location, and preferably contact your nearest university, right? And contact the anthropology department. And there will be someone like me or Dr. Connolly that deals with this all the time. And they can kind of walk you through the steps about curation and obsidian sourcing and sort of the right thing to do. So that's my best advice: is contact your nearest university, please. Archaeologists and geologists are very nice and they like, helping people. At least the majority of the people that I talk to like helping people. And so there's this stigma where people are scared to talk to people. Don't be scared to call up the university. They're not going to steal your artifacts or your geology. And you'll find out a lot of really good information if you talk to them. So
question, can you run over the Newberry explanation again?
I can give a speed run. It has a lot to do with obsidian. So Newberry and Glass Buttes are basically the number 1 and number 2 largest provinces of obsidian in the entire world. So Glass Buttes is a series of domes where obsidian is a collapsed stratovolcano. So the stratovolcanoes and the Cascades have different sort of obsidians than the high lava plains domes. Just wanted to say that. Basically, what's happening is the subduction zone is causing the Cascades to form. That is a later process. The Yellowstone Snake River hotspot migrated from the McDermott calderas where it started, and you can track the ages. So it's moving over to Yellowstone, and it's getting younger as it goes from Oregon to Yellowstone. What's happening is that hotspot, as it's migrating, is melting other magmas and causing a magma plume to then cause another smaller hotspot in Oregon. This magma plume hotspot is what created the rhyolite domes and the obsidian domes and the high lava plains like Glass Butte. And that's actually trending. It's called Younging trending volcanism from the west to the east. So it's east-west young and trend in volcanism, and that can be tracked. And so we know that its terminus is at Newberry because Newberry is the youngest obsidians that have been erupted. And so therefore, if the obsidians are part of this process and the youngest obsidian is at Newberry, we know that sort of the culmination of this mantle plume is basically interacting with the Cascades. And essentially, we think that it kind of get caught at Newberry and that Newberry will sort of stop the obsidian sort of trend. But that's more speculative.
So I worked in northern Arizona, and when I was first working down there on the Coconino National Forest, the archaeologists were talking about the obsidian, and this was back in the early 1980s, that they figured it was sourced out of the Great Basin. So in your travels with XRF, have you looked at any of the obsidian that has wandered outside of the Great Basin neighborhood to figure
Yeah,
out?
it's amazing question. Amazing question, amazing question. So, two parts to that. So Oregon, we have a lot of influence from northern Nevada and California. There's a big obsidian deposit called Glass Mountain by Mount Shasta that's really, really cool. I
Yep.
actually have, some samples from there. But in terms of even greater than that, Dr. Connolly has an amazing article from 2019, I believe, that talks about there. So, of all the obsidian in British Columbia, 25% of it comes from Oregon. So, of the 25% in British Columbia that comes from Oregon, there's four main sources: Glass Butte, Newberry, Obsidian Cliffs, and the Strawberry Volcanics. And the Strawberry Volcanics is where I did my geologic mapping. And it's essentially, Dr. Connolly talks about the headwaters of the John Day River. And there's a theory, his theory is that through obsidian sourcing, we're literally tracking them trade obsidian up the John Day River from Strawberry Mountain all the way up into through the Puget Sound into British Columbia. So that's sort of the power of obsidian sourcing.
So that's headed north, but what about the southern end of it, like northern Arizona and Utah?
There seems to be a blockade basically in Nevada because what's happening is Nevada, the climate dried up so fast, I believe, that Hughes actually writes about how in Nevada, there seems to be a closed sort of loop in the Great Basin. And there's actually these different loops where if you essentially have a big desert and you have obsidians on either side, that they sort of just travel in a circular pattern following the game.
Okay.
And so a lot of it doesn't really make it out of Nevada. And this further isolates, Southern Oregon. So in terms of Arizona and Utah, I believe Arizona and Utah share a lot of materials, as well as Southern California.
Okay.
But
Because
there seems to be some geographical, constraints.
yeah, that was a theory at the time with the Sinawa and Anasazi, and that's what they were looking at the time. But that makes sense. And this is the 1980s.
So I thought it was pretty interesting. You had said that you assume that rhyolites that come from a specific location are homogeneous, but the processes that create rhyolites can be incredibly variable. And I I'm just curious, how is it that you can make that assumption, especially if you're doing your sourcing off of so few elements? So how is it that you can assume that rhyolites from a single locale are homogeneous if rhyolites are such a complicated thing to create?
Right. So I kind of wanted to have a slide about this, but it's a little bit not my subject. But this has to do with sort of rhyolite petrogenesis, and essentially obsidian and slash rhyolite form. This is in the Ford PhD, by the way. They form through two major processes. One's called magma maturing, and the other one is called essentially where the magma matures and then it erupts and certain elements get erupted off. The lighter elements get erupted off. And you need both those processes to form a rhyolite sort of magma. So when that process happens, certain elements are left because the lighter elements literally get sort of burped off in these subsequent earlier eruptions. So when the rhyolites actually form these obsidian or rhyolite domes, the, sort of the dome is essentially the contents of the chamber. And the magma chamber actually has relatively consistent sort of ratios, which is another aspect of obsidian sourcing that this is one of the it's called the sourcing postulate, and it's that the ratios of elements stay consistent regardless on which part of the dome you look at. And they went into this on Glass Butte to make sure that this is true. And there are slight, chemical differences in the trace elements, but they're not in like a great enough percentage for it to matter in the grand scheme of sourcing different sources.
That's interesting.
Those are
Can I
bad
ask a
accusations.
stupid question? Well, no, it's not a stupid question, but it's one that I think Gabriel and Alyssa can address, because I have in my mind that magma chambers usually have crystals in them. They're phaneritic or whatever. But then you get this with the obsidian and the rhyolite, you get something that's homogeneous as it erupts and then cools quickly. Is that a subset of typical rhyolites, and how frequent is it? And is it the sort of thing that Gabriel's talking about and Alyssa looks skeptical about?
Right. So magma chambers are. We have a lot of ideas of what happens,
Yeah.
but the difficult thing about magma chambers is we can't observe them. We can only see kind of what we interpret to be like the frozen ones that are left behind as plutons and whatnot. There's a lot of debate, and I think it can also depend on like where these things are at, composition and whatnot. But a lot of the talk is that there's actually a very small percent of these magma chambers that are molten at any given time, and that there's a lot of the melt can be kind of, it can be like really, if you think of like a sponge holding water, it's like you still have the sponge there, so it's like it's in between things. It's not just free floating. So yeah, that's it's a complicated question.
Well, and what I've seen about with my own personal research with the XRF machine, because I'll literally start collecting obsidian from the base and then sort of collect, obsidian or rhyolite as you work your way up the dome or the mountain. Across an entire mountain, samples are relatively consistent. So within my own personal research, I would 100% say they're consistent. They vary by, tens to single digits of ppms, but that's not enough ppms to actually affect the charts on the sourcing. So there is a natural variability in the elements, like Alyssa's saying. But in terms of like, knowing the difference between Glass Butte and strawberry rhyolites, it's very clear. But in terms of within the Glass Butte, there can be, especially for Glass Butte specifically, there's a wide distribution of ZR. And that creates issues. Yeah.
Okay.
And that literally, that directly creates issues for Glass Butte. And so for Glass Butte specifically, they like to use EU versus CS plots, which you need ICP-MS. So for my study, it's not as helpful because I can only use XRF. So I'm still working on that part, everyone. That's one of the major issues with Glass Butte.
So EU and CS would be europium and cesium. Yeah. That's interesting. Yeah. I think the fact about this of having to be non-destructive has got to be pretty frustrating. But I know that even in studies where they can be destructive, a lot of these studies still are going to lack ICP-MS analyses anyway, which is what you've been hearing me talk about for the past 5 years of research.
It's really expensive.
Yeah, it's just not always there. I'm curious if you could use another proxy for europium though, because europium is going to follow the behavior of other elements. And so is there a proxy you can use instead of, because I know people will use cesium versus yttrium instead of
Yep, Y is another big one. And then
lanthanum versus
NB, whatever NB is, I always mispronounce it.
niobium.
Yes.
But thinking a proxy, because if you're trying to think of why europium would be high or low, it's probably going to be tied to feldspar fractionation, most likely. Well, I guess in a rhyolite, it could be either an alkali feldspar or a plagioclase. But it's like I'm wondering if you can use another something that would fit in that same site, like mineralogically.
So am I gathering that if you used XRF, you might be able to see things with a resolution, you'd see a greater variety of element comparisons that, for example, Alyssa has been using in her research? Um,
I use XRF
Other
and
way around.
yeah.
ICP-MS.
Okay.
Yeah,
Other way around.
it's just the element availability, because the two methods are different. It's just how they collect the element information. ICP-MS just has a wider, it has a larger amount of elements that it gets, but XRF is much more readily available.
Gabriel, great job. That
Yeah,
was
thank you
fantastic.
guys.
Really excellent presentation and fascinating. And it's so important to see the connection between this and the conversation we're having about sort of indigenous issues, to see something that actually really relates to understanding that history, because it's hard to, for both political reasons and just historical reasons, it's a hard thing to kind of get a grasp of. So
Well, I really appreciate it, you guys. Thank you all very, very, very much.